next up, I would like to introduce Mencken Davidson, who will be presenting automating the modeling of production networks in virtual labs. Mencken is a principal network architect at Blue Cross Blue Shields of North Carolina and formerly a network architect at AT&T and HP. He spent the past 25 years designing, building, operating data communication networks in the campus, data center, wide area, and public cloud context. Welcome back to Nano, Mencken.
Thank you very much, Michael. So I'll go ahead and address the elephant in the room. Obviously, we're all wondering, how is it possible that the only and premier mission-driven, not-for-profit healthcare organization in North Carolina has been absent from NANOG all these years? The short answer probably lies into the answer to the question I got when I said to my managers, hey, would you like to pay for me to come present at NANOG in February? And they said, what is a NANOG? So, yeah, happy to expand both of our social circles to be here. So, let's see here. I think I got my bearings. So, just to be clear, I'm not going to talk to you about network automation. I'm going to make a distinction here. I'm going to talk about how we approached the subject of, or approached the topic of automating the modeling of production networks in a virtual lab environment. A good analogy that I thought of last night as I was falling asleep was maybe thinking about it in terms of the difference between trying to make a sketch, just like illustrate 5 different things and give them to somebody and have them, based on that sketch, go build those 5 different things. That's what I think of as kind of the problem shape of network automation. You know, when we talk about network automation in general, we're often talking about trying to take a bunch of concrete, well-defined, well-regulated systems and abstract them into some common language, like GNMI, open config, Yang models, and all that, that roughly approximate their inner workings, and then take that abstraction and apply it to a bunch of other physical substrates. We're not doing that. What we're interested in is kind of sidestepping that additional layer of abstraction, and then it's the opposite of abstraction, de-abstraction. It's more along the lines of take a picture of it, get a photorealistic description of the run state of your environment, and then just print out a copy of it. We often hear that described as digital twinning. I'm sorry, my kids would call it digital twinning, of a digital twin, I guess. But that's kind of the difference between the problem we were trying to tackle, or I was trying to tackle, and a lot of the more hand-wringing, hair-pulling talk about network automation and the challenges around it. So I think I just used up my budgeted time for preamble, so I'll skip the preamble for the most part, and I'll get straight to target audience. So luckily, it's a fairly small audience today, so the target probably doesn't matter all that much, but if you have non-production hardware, like hardware where you're actually currently emulating your production networks, this whole talk is just way below your pay grade, but it's nice to have you here. For the rest of us, virtual network labs are quite often the next best thing. And there we go. So I'm going to talk to you about the cases for and against virtualized network labs. And then I'll kind of get into a overview of a case study methodology for how we tackled the problem. And we'll do a summary, we'll talk about design decisions, functional analysis, get into a bit of the brass tacks of the technical solution, and hopefully linger a bit on lessons learned, leave time for questions and answers and thank yous. All right, so the case for virtual network labs. Learning, studying, exam preparation, that's old hat, boring. If you've been at it for a while, you probably got started using virtual network labs to do things like study for certifications that, depending on how much gray you have in your beard, you let lapse a long time ago anyway. That's not what I'm really going to talk about today, but obviously kind of the gateway drug for a lot of us for virtual network labs. Change modeling, change validation. That, I think, is a really compelling use case that carries a lot of weight today. I know I always felt a lot better headed into a change window if I had actually gotten rigorous syntactic validation on the configurations I was trying to apply. Desk checking, it's good. I wish I was better at it than I am, but I'm just not. And even doing that in a single device context, I always found valuable, but being able to take that and scale it to actual systems of networks, say an entire layer 3 leaf and spine fabric, there's a lot of value to be had there. And that relates pretty directly to troubleshooting as well. Say it with me, the cure can't be worse than the disease. There are tons of problems that just fester in our production environments for a long time because most of the diagnostics that we want to do to actually find the root cause are more invasive than we can take. And physical labs have a long tail in terms of getting them up and running, especially if you're relying on vendor support to lab it in their network because you're a regional healthcare payer and you don't have the money for mountains of extra gear. So, look, short version of all that, virtual labs can be set up a lot faster than physical ones, which hopefully improves your mean time to resolution. Also, I think in the pro column for virtualized network labs, cost benefits, or the cost-benefit ratio. Virtual labs have really low costs. Doesn't cost much at all to run a containerized version of a Nokia switch, or even a VM version of a beefier F5 LTM or something like that. But the benefits, on the other hand, they stack up pretty quickly. In terms of FTE hours you actually spend doing things on a day-to-day basis like peer review of basic syntax for command configurations and the rework of changes that make it through syntax validation but have to be rolled back because of just logic errors. If you're using virtual network labs to model changes, you're going to decrease the incidence for both of those. And like I mentioned in the previous slide, mean time to resolution for tough to diagnose issues can also be reduced. A virtual in-house lab, maybe you can set that up in a few minutes, which I'll talk about later on. But even without the work we did, we could set up a virtual lab that would give us real diagnostic value, say in a few hours or a day, as opposed to waiting maybe a week or more for a vendor to be able to do that for us. All right, so if that's the case for virtual labs, I'm talking about the case against virtual network labs. Fidelity, the VNF version of your product is not identical to the physical form factor. It can look and feel very similar, and in our experience at Blue Cross NC and my wider experience in other places, the fidelity isn't perfect, but it is often remarkable. But again, not perfect. There are always going to be the corner cases. There are going to be the nuanced functionality that you can't replicate in a virtual lab. All right, so I kind of got into more detail than I think I needed to on the rest of that slide there. But the fidelity goes away quite often because you're doing x86 software trying to model what's happening on custom silicon, and you can get a model, but it's not going to be perfect. And aside from that, there's the fact that when you're doing any kind of lab environment, you can generally do a pretty good replication of the stuff you own, that you have administrative control over. But at the end of the day, why do we have networks? It's to connect to other things. And oftentimes the problems we're trying to chase, they involve us interacting with other systems that we don't control. So to the extent that that's an argument against a virtualized network lab, I think it's really an argument against labs in general. All right, so I guess, full transparency, I'm having a hard time really making the strongest case against virtualized network labs, but Yeah, at least I'll admit it. All right, so I think this is our final ding against virtual network labs. The level of effort increases exponentially along with the size and scope of what you're trying to model. It's relatively linear in terms of the number of devices, but it's downright exponential when you start accounting for the number of interconnects between those devices. So bigger scope in terms of what you're modeling means higher fidelity, but it also means drastically increased level of effort in configuring it, at least if you're doing it manually. And then, that's wrong. I guess that was the penultimate ding for VNFs, or virtualized network labs. Final argument against them is just the availability of virtualized form factors for your devices. If there is no VNF for the devices that you have on your network, you're not going to be able to use them in a virtual lab. Too bad. Again, you've probably got your own hardware, got your own lab, teams, you can just deal with that. But it would be a good reason not to spend a lot of time thinking about how to automate building a virtual lab if you couldn't build one in the first place. All right, so let's move on. So I'll get into the kind of case study portion of the talk. So where we started was we had 2 co-location data center footprints. We had kind of partially migrated to using Netbox as our data center infrastructure management / network source of truth platform. I know source of truth is at this point a pretty loaded term. We weren't really, I'll say we were trying to use it as our authoritative record of network design intent. Wasn't true in the sense that it necessarily represented what was happening on our network. It was true in terms of that was what we wanted our network to look like, which is an important distinction when we talk about the process we automated. And we also had the GNS3 network emulation platform up and running in-house on a kind of moderately robustly endowed VM. And what we wanted was to get a much better juice to squeeze ratio out of our GNS3 tool. We wanted to spend less time building virtual labs and more time using the virtual labs. And where we landed at the end of our little adventure was we have a homegrown Python package called pdvnetlab, and it does all the heavy lifting for us in terms of actually collecting the run state data from our devices, converting it into a VNF-friendly format, and then instantiating the virtual lab. We also have a homegrown plugin for Netbox that will be a front end for that pdvnetlab package, as well as provide inventory backend to let us choose what devices we want to model. And what we saw after implementing it was, ballparkish, about 2 orders of magnitude decrease in the level of effort for our engineers to model things, specifically to model our data center networks in the virtual lab. And I have some wrong numbers on that slide, but where we ended up as of last week anyway was now, instead of it taking an engineer maybe a couple of days, if they wanted to go in and try to model our layer 3 leaf and spine EVPN data center fabric, now they can do that in just under 2 minutes on 58 on one of our data centers fabrics, which happens to have 48 switches running on it. So I think that was I thought that was a pretty good result. But what that looks like for us is what I call easy in, easy out. So on the front end side, an engineer will log into Netbox. They'll click the P2V button. They'll get a nice little form. They get prompted for credentials, point and click, choose a list of devices they want to model, choose which DNS server instance they want to use, in our case, just the one, and give it a project name and click go. And just wait a couple of minutes, and then we get a nice, lovely virtual lab built out for us. There's a picture of what that looks like on the GNS3 web UI. You'll see we've got a bunch of switches there, and we've got a bunch of connections between them. So that is kind of the high-level overview of where we started, where we ended. So I'll spend the rest of my time talking about how we got there and what we learned on the way. So initial design decisions, we decided very early on that we were going to want to use GNS3 as our virtual lab platform. As I mentioned earlier, we had it. It was running. It was available. That was an easy decision. We decided to develop in Python, mainly because it was the language that I won't say I knew the most or had the greatest facility with. It was more like it was the language that I looked like, or I had the least incompetence in. But after deciding we were going to use Python, next decision was to use API interactivity with all of the system components wherever we could. The main concern there was I wanted this to last longer than a week. I wanted it to not be something that I would build and give to the engineers, and then if I moved on or they went somewhere else, they would just, somebody could breathe on it and it would just fall apart. Using APIs to facilitate all the interactions and the workflows inside of the system mean that it's more decomposable. It just so happened that we had Netbox running on the same host that we had GNS3 running on, and that GNS3 was running all of the containers locally on that same host. And there was a very strong temptation to do a lot of things by just writing to the local file system on that host. But if we did that, maybe it would have been a bit quicker to build, but then it would be, a relatively big black box that we couldn't refactor if we wanted to. Using API interactions, this way we can move Netbox away from the GNS3 server if we want to. We can decompose the GNS3 stuff itself so that we can have it run containers on a separate host running Dockerd if we wanted to. Think for the future, I guess, was a design decision there. And then we decided that we wanted to build the virtual labs based on the actual run state of the devices we were modeling, as opposed to, say, modeling them based on the network source of truth, as opposed to the intended configuration state. I had mentioned earlier that we were, at the time, partially migrated to using Netbox as a source of truth, and I had also talked earlier about the difference between taking a picture and printing a copy of it versus drawing a sketch and showing it to someone else and ask them to draw a sketch. The use cases we had in mind for a virtual network lab required maximum fidelity and didn't so much require abstraction and portability. We weren't really interested in trying to build a network lab where we could model 40 Arista switches and get the same functionality on 40 virtual Nokia switches. And because of that, it was a shorter path to, and really a more accurate path for us to try and get the run state data about the devices we were modeling directly from them. We saved the layer of abstraction and recomposition and the loss of fidelity associated with that. We saved the development efforts of trying to figure out how to translate, say, Arista run state into pure GNMI and Yang models, and how to translate that back into Arista run state. And then we decided that we wanted to use open source code and produce open source code wherever possible because we're good citizens. And we wanted to use container form factors wherever possible, just because they have a lower footprint than VM-based form factors do. All right, so next step for us was task analysis. So if you can describe it, you can automate it, but only if you can describe it precisely and accurately. So there's nothing special about the process, nothing innovative about the process we took there. We were lucky. Modeling our production devices in a virtual lab was really pretty deterministic. There wasn't a lot of variance, wasn't a lot of depth to the decision tree. So I made it a good candidate for automation. And the task analysis process was at a high level. We wrote down what we did, kind of step by step. find some random 10-year-old, give them that list of step-by-step instructions, ask them to execute on it, go back and see what didn't work, add those steps in, repeat with another fresh, empty-headed 10-year-old until you get a process that actually works, which I can do a good impression if anyone's interested, of somebody who knows absolutely nothing about networking, as can my 10-year-old daughter. So what that looked like for us was we came out, I sat down with the engineering team, and we came up with an initial iteration of what our virtual network lab process looks like. High level, choose the list of devices, gather the run state from each device, then loop through the list of all our devices, sanitize the configurations, sanitize them in terms of get rid of confidential data that we don't want leaving our production network, get rid of OAM and P type stuff that we're not interested in modeling in the first place, get rid of hardware dependent stuff that at best would do nothing in the virtual network lab, and at worst would actually stop the virtual devices from running at all. And after we would loop through the devices and convert the run state data. I apologize, I seem to have got myself lost in my slides. Let me back up for a sec. Yeah, there we go. And we would go in, create a new project in our virtual lab platform. We loop through the devices again. We create all the devices in the virtual platform, and then we push the run state we had captured into the virtual devices. And then finally, after we've captured the run state, we loop through the list of all the interconnections that we had collected along with the device's run state and push them into the virtual lab. All right, so I got about 10 minutes left. So brass tacks, what did it end up looking like? We have a repository on GitHub called p2v-netlab. Source code's all there. It's published with a modified BSD license. We used the pyproject.toml pep518 format for build specs, and we used something called setup tools SCM for version management. We'll talk about that in lessons learned. We also have our documentation hosted on the same GitHub repository and GitHub pages. We ended up using Sphinx to generate documentation, the Auto API plugin for Sphinx rules, by the way. And the package itself is published on pypy.org, so you can just install it with pip if you are so motivated. So within the p2v-netlab package, there are, we've got 6 total Python modules. We've got a data classes module where we've really only defined 2 data structures, the concept of a switch and the concept of a connection. Each of those has their own properties. Switches have properties we care about, a number of interfaces, device type, software version, configuration, etc. And then connections are pretty straightforward, just point A, point B, device name, and interface identifier. Second module is the main module. It's the entry point for the lab, entry point for the package. It's called p2v-netlab, and that runs the overall work. That's where the overall workflow for creating the lab lives, and it orchestrates the next 3 modules. We've got an Arista polar module, which collects run state data from Arista switches. We've got an Arista sanitizer module that converts the run state data from those Arista switches into lab friendly. And then we've got our GNS3 worker module, which actually does the build out of the virtual lab. And we've got a tiny little module at the end called p2v-netlab CLI, and that's just there to provide a CLI one-liner entry point for the module if you don't, if you want to get the benefits, but you don't necessarily want to actually go open a Python interpreter or try to invoke it directly programmatically. So lessons learned. Oh, there we go. Sorry, I was trying to keep track of my time remaining. So lessons learned. The first thing that we figured out was that the async I/O portion of Python turned out to be critical for us. In the workflow that we had described, we're doing things that we're doing three main things, I think, that really don't need to be serialized. You know, we're going out and say we've got 50 switches and we want to collect run state for them. You know, it doesn't do us any good if we collect data from switch number 1, wait till we're done, collect data from switch number 2, wait till we're done, et cetera. Those are, you know, there's no interdependency between those. But if we're not using an async model for our code execution, we do that. We do end up waiting for one to finish and the next to finish and the next to finish. So async I/O is how Python provides cooperative multitasking, and that turned out to be really important for us. So one of the things, or some of the interesting insights we got out of this project were that async I/O lets you, well, I mentioned that it provides cooperative multitasking for Python, but specifically, especially with the AIO HTTP module, it provides a shared context where you can use a single, say, TCP socket as your shared context, and you can put a list of tasks into that, and it'll go through and it'll try to execute each of those tasks. But once it starts each task, it'll step away from that task. You generally want to use I/O-bound tasks in this model, like say it's an API call to a switch an API call to GNS3 to create a new node. It'll fire that request to the API, and it won't wait for the response before it moves on to the next task, which will be, in this case, to send another API request to create a second node. And we can do all that in the context of a single TCP socket running in a single thread with a lot of other processes, but we get the advantage of the cooperative multitasking. We get the advantage of being able to have, say, all 50 API calls open at the same time, all executing on the server side at the same time. And if it takes 4 seconds for our GNS3 server to come back with a response saying, okay, I built your node, maybe that's the difference between it taking 7 or 8 seconds to respond to us for all 50 nodes versus it taking a few hundred seconds to respond for us. And that works really well. That turned out to work really well for us. We got great improvements in how long it took to do stuff. We got great improvements in terms of resource utilization on the GNS3 server. You know, before we started using async I/O, you know, we were crushing ourselves on both ends. Ton of sockets, ton of sessions, ton of TLS, just a ton of extra work we didn't need. And that worked out really well on that end. The other interesting part of it we found was that it doesn't work so well when we're, say, making calls to 50 different devices at the same time. In phase 1 of our workflow, phase 2, where we're collecting data from our fleet of switches, there's no way we can talk to 50 different switches on the same TCP socket. And we were lucky enough to live in a point in history where I think it was around Python 3.8 maybe, where they introduced the 2-thread function in the async I/O module. And that lets you actually, instead of using an individual socket as your shared execution context, it lets you actually allocate separate threads in the separate threads managed by the Linux kernel as their own separate execution contexts. So that meant, in our case, we're able to do something like open between 20 and 50. You got to tune this based on your resources, but lets us, while we're getting ready to, say, poll 30 or 40 Arista switches, lets us do that cooperative multitasking way using 30 different threads in the kernel so that we can actually have those 30 different sockets running at the same time, and the individual threads operating in the kernel are doing their own cooperative multitasking dance. But long story short, it lets us get through each of the phases in that workflow without having to deal with serialized dependencies as we go from item A to item B. I got ahead of myself on that one. The other big lesson learned for us was related to smuggling files into the virtualized devices. Since we were working mainly with Docker since we were working mainly with we were working exclusively, I should say, with containerized devices. Sorry, I keep trying to check the time and getting a bit confused. Since we were working exclusively with containerized devices, the question arose, how are we going to get our configuration data into a container? Again, we wanted to do as much as humanly possible through API interactions so that the elements of the system would be decomposable in the future. And that meant that we didn't want to do what we had been doing in our manual workflow days, which was we would just go find the section on the underlay file system that hosted the volume for each container, and we would just copy a file directly into the underlay and then turn on the container and be good to go. We found out that the Docker API does let you actually write a file to a container's file system directly. The container doesn't even have to be running at the time, which is great. Made life a lot easier for us. We also found out that it only lets you write that file to the root volume. And unfortunately for us, all of the files that we really care about in terms of the run state we're trying to emulate, they all live in a separate Docker volume that gets mounted at runtime on the container. As far as we could tell, Docker APIs don't give you any way to write directly to a volume object. So what we ended up doing was using the Docker API to send a file to each GNS3 virtual node after it had been created. So the workflow itself, I don't have time to get into it, but there are slides at the end of the deck if anyone wants to go look at them later or talk to me about them later. But the workflow on the GNS3 side is we actually loop through all the devices, create them via the GNS3 API. While we're at it, we grab the actual Docker container UID for each node that's been created. Then once that's done, we loop through all those Docker node IDs, and we actually make an API call to Dockerd and its API to send our converted configuration data directly to the Docker image. Then we turn on the Docker image, and then we actually use the Docker exec API call to run an MV command to move it from the root volume into the, in this case, the mount flash directory that's been attached to the container when it ran. All right, and I think that's all I had to say about Docker API. Oh no, there was one more important lesson learned for us, and that was whoopsie when Docker was running as root on our GNS3 VM. In all fairness, I think this is probably our fault, not Docker's fault, or maybe a little bit of both. But in our virtual lab platform, Docker service is running as root, and when GNS3 goes to create, when Docker 3 goes to actually create a Docker image via the Docker CLI, via the Docker API, I should say, that container ends up running with a number of root privileges at the host level. And specifically the one that mattered was the Arista COS containers set the FS I-notify max user instances value to 1256 when they run, which is a very healthy value, Arista should know, right? For a single Arista switch as it comes online. Yeah, I guess they don't need to touch more than 1,200 or so files at once. Unfortunately, every time an Arista container ran on our platform, that FSI notify value was getting set on the host at the same time to 1256. So, this actually predated our adventures in trying to automate this process for a long. In trying to figure out how to automate it, we solved a scalability problem of our own, which was just that we could never figure out why we couldn't get more than a dozen or so virtual switches running on our GNS3 server. Turned out the main reason for that was because the host itself had the FSI notify max user set way too low. And we were getting around it for a long time by just kind of staggering the boot order for our virtual devices. Most of the concurrent file touches come when the container comes online. For the most part, during steady state, it's not touching 1,200 files at once. But what we wound up doing was instead of actually fixing our implementation of Docker, in that environment so that the containers didn't actually have root access, or were making it so that they could not impact the host setting for reasons, mainly involving internal siloing. We just when we import Arista containerized EOS images, at the time we import them into the local Docker repository, we just go in and modify that setting in the underlying Arista image. Just add a couple of zeros to it so that every time they run and they do change the host settings, they make it a nice big number that doesn't lead to any problems down the road. And then two last things we learned. Sphinx is great for documentation when you're doing infrastructure as code or just GitHub stuff in general. And specifically, the Auto API extension is really fantastic. Got a quick snippet on this slide here showing what the Auto API generated documentation for our apply sysmac function in the GNS3 worker. In the GNS3 worker module looks like. You get a nice, relatively human, non-dev person readable explanation of what the function does, what the input parameters are, what it returns, and even a link directly to the source code itself, along with the along with nothing. That's it. But we found that to be incredibly useful. It's been my experience that most people don't like writing documentation in the first place. And as we were trying to kind of stretch our wings and move into more code-based automated workflows, being able to reduce the friction associated with documentation was a big win for us. And then the final thing we learned was that GitHub Actions are good friends in that endeavor as well. We wound up using two GitHub Actions workflows in this project. One that just refreshes the documentation and publishes it to GitHub pages every time we issue a commit in the repository, and then the other that publishes, when we actually create a GitHub release, actually publishes the package to pypy.org and also let us consolidate version management in the GitHub UI directly. That utility that I mentioned, I think on slide 3, that I just forgot the name of, I think it's setup SCM, lets us use the versioning attached to a GitHub release as the driver for the versioning that gets published to pypy.org, and saves us a lot of muddling around between 4 or 5 different points and 4 or 5 different pieces of code every time we want to publish a release. And the less time we spent, dotting I's and crossing T's, trying to keep release versioning data synchronized, the more time we could spend actually getting it to work. So kind of double tap on the trigger there. But what comes next for us? Timing's just about right. I think there are a number of core functional enhancements that the path is pretty open for. We want to integrate additional virtualization platforms and network operating systems. Obviously, everybody likes Container Lab this year. It should be relatively trivial for us to start on the output side generating Container Lab configuration YAML. I think it's JSON, whatever, JSON, I guess. And likewise for additional network operating systems, they're Nokia, Cisco, Sonic, there's plenty of them out there. And because we're taking pictures, photographs as opposed to drawing sketches, the level of effort involved in trying to capture that should be a lot easier. Just to beat that analogy to death, I'm not an artist, but if I were, and I spent years learning how to draw the human face in remarkable detail, and then someone gave me a majestic landscape and told me to draw that, I'd probably have to retrain myself quite a bit in terms of recognizing the different patterns and how to express them in a way that the human eye and brain can actually interpolate. Whereas if I've got a camera, I know how to take a picture of a face, and I know how to take a picture of a landscape, and I know how to take a picture of my shoes if I want to. And the other near future, I hope, enhancements include trying to create, what do I call them here? Trying to create, generic partner nodes for the devices that we don't manage directly, that we don't actually have the ability to pull for run state, to the extent that we're interested, say, in BGP behavior in our network. We want to be able to create generic BGP nodes to represent devices that our network is attached to and mimic their behavior as best we can. All we can really do is take a picture of what their steady state behavior looks like from a neighbor perspective. But yeah, that's certainly better than nothing and kind of increases the fidelity marginally and just requires, if it's going to provide us any value, that we go into it with a well-announced, enforced understanding of those limitations. Also, I'm very interested in trying to see if this makes more sense integrating directly with Autobot for probably for the majority of the data structures and also for front end. And more importantly, more to the point of me being here today, we want to try and build some community around this. I'm the only one who's really worked on this at all, and I'm kind of taking it with me as I leave Blue Cross NC. It was more of a personal project, a gift to the engineering team, and I would very much like to keep it going. And towards that end, there's a where to engage slide here that has links to the repositories and my GitHub profile if anybody wants to poke around a bit. And that leaves us, I think, over time. I'm not quite sure, but if there are any questions, I'd be happy to stick around and answer them. I do thank you all very much for your time. I would also particularly like to thank Steve Ulrich and Alex Latsko for their shepherding and review. Their editorial guidance greatly improved the content you saw here today, despite everything I did to try to stop them. Thanks again.
Thank you, Mencken, for your presentation and time today.
Oh, thank you. Oh, look, a question.
Oh, sorry. Yeah, we have a question.
Hey, Chandler Willoughby from Bandwidth. First of all, cool to see a fellow North Carolinian giving a presentation here. Second thing, one of the issues that we historically had when running virtual labs was the, artificial restrictions that vendors were putting on throughput limitations. Obviously, we're never going to get anywhere close to bare metal hardware performance when it comes to virtual labs, but many of them were limiting it to like kilobits per second, which made testing things like load balancing or rate limiting difficult. I was curious if that's kind of still the state of the industry, what your experience has been with that, or if that's kind of just out of scope for the virtual labs that you guys are running.
A little bit all of the above. I think I beat around the bush rather than saying it directly, but the scope of this up to this point has only been modeling Arista devices, and from our experience on the consumer side, performance on the Arista CEOS platform in terms of capacity has improved relatively steadily, a bit more distinctly within the past couple of years. For the life of me, I can't remember the actual names that Arista uses for the forwarding engine on CEOS, but I know relatively recently they changed from the old one to the new one, and the new one does seem to be a bit more performant, but also, any kind of capacity stuff was completely outside of the scope of our use cases for the virtual lab. But I suspect that we probably just hadn't got to the load balancer use cases yet, and I don't know how those would have shaken out.
Fair enough. Thank you.
Oh, thank you.
Hi, Tim Novacek, All Points Broadband. A little bit of a side question, kind of about the source code in your organization. A lot of companies don't have like programs of open sourcing tools that they write internally. Did you have any problems convincing your organization to allow you to open source something that may have been covered by like a proprietary inventions kind of signing that many employers make their employees sign. Anything you invent while on the job is our property. Like, do you have any problems with that?
No, I did not. Mainly because I made sure that I started this on my own time, and I put it out there as an open source licensed initiative. And honestly, I really didn't spend company time working on it. So there's your answer. But I can tell you kind of anecdotally, I wound up brushing up against Blue Cross NC's relationship with open source licensing about a half dozen times over the past few years. And like a lot of organizations, we don't handle it in a very coherent or cogent way. For what it's worth, the extent of the friction on our end generally seems to be related more to the adoption of anything in a production capacity or in a business impacting capacity without the contractual relationships to guarantee us what leadership would deem an appropriate level of support, and more importantly, would allow us to diffuse financial risk, to actually associate financial penalties with problems that don't get solved. But since this is a lab environment, none of that, nobody hit the brakes on that anyway. So I guess it was a two-prong approach, build it open source in the first place and then pull it in, and don't do anything that anybody's going to care about.
Thomas Scott, CoreWeave. Number one, thanks for presenting on this. This is a topic that I know we've had multiple iterations on at NANOG over the years, and it's always cool to see a new approach. Two questions. First one being, and I think you kind of answered it as GNS3 being the devil you know. But was there any thought given to any other iNet lab or container lab or any of the other more open source ones that have emerged over the past few years?
The short answer is no, not really. The company standardized, or not standardized, the company, Blue Cross NC brought in GNS3 about 5 years ago. And when I say brought in, I mean, we just went through the technology adoption process to the point where we put a record into a system we call Aardvark, saying this is an application we use and it's licensed this way and this is that. But at the time we did that, the other platform we seriously considered was EVE-NG, and I don't remember what the pro-con balance sheet for those two looked like 4 or 5 years ago. But short answer to your question is yes. And as I mentioned towards the end there, I very much think that it's in the cards that I'll be adding integration for other backends like Container Lab and EVE-NG as time permits.
Very cool. Follow-up question to that is, did you have any sort of version control that you built into this as far as like the actual labs that you produced? So for instance, it sounds like your scope was more concerned with taking a live snapshot and creating a lab. Okay, that was my curiosity.
Yeah, so no version control on the lab environment side.
Very cool. Thank you.
I'm glad you appreciate our lack of version control. Okay. Again, thank you.